Welcome to the first lecture. In this lecture, we're going to get some introduction and motivation for cloud computing and software architecture patterns. We will first discuss the specific types of design problems we're going to solve with those patterns. After that, we will compare what we know as software design patterns and the unique software architecture patterns we will learn in this course. And finally, we will narrow down our scope to architecting on the cloud and briefly talk about some of the benefits of cloud computing, which we will learn to leverage, as well as its limitations, which we will learn to mitigate throughout the course. So let's talk about the design problems we're going to solve. When we get the requirements for building a brand new software product, we can divide those requirements into three categories. The functional requirements, which dictate the functionality and features of the product. The non-functional requirements, which we call quality attributes, that dictate the quality measure of how well our system functions. This includes things like performance, scalability, availability, reliability, and so on. And we also have the system constraints that limit our design choices to a subset of technologies or APIs. We're going to ignore that third category for the purposes of this course. Now, if we look closely at the first two types of requirements, we can notice that the functionality or the features of the product are really the unique aspects of our system. For example, if we are designing a new ride-sharing service, video on-demand system, or even an online video game, it's the features that we want to deliver that differentiate our system from its competitors, but also from any other software system in existence. In other words, it's the business logic and the user experience that defines our software product to the outside world. On the other hand, if we think about the quality requirements, it turns out that many companies delivering products that functionally have nothing in common are facing the exact same challenges. This means that they can also benefit from the same solutions. For example, if we look at an online store, an online education platform, and an online dating service, those systems have very little in common in terms of functionality. However, on the quality requirement side, all three have similar performance requirements, since they all interact with the user through a web-based UI or a mobile app. Also, if they cater to thousands or even millions of users, they would also have very similar scalability challenges. And since they all have data to store, process, and display to the user, they may benefit from similar architecture patterns for processing and querying data. Similarly, we may have two software startup companies in completely different industries. One may be offering a user-facing social media product, while the other may have an online productivity suite of tools that they sell to businesses. However, both of those companies have grown so much that they are now facing organizational scalability challenges, and they are now struggling in their migration from a monolithic architecture to a microservices architecture. So while both companies have nothing in common externally, they can benefit from the same scalability and extensibility patterns internally. And finally, all companies nowadays are expected to be highly available and reliable. So software architecture patterns that help us handle errors as well as quickly and safely release new features while still providing our users with uninterrupted service can benefit every company. So it would be really nice to have a set of common patterns that we could easily apply to the architecture of any system. This way, we could really focus on building the innovative functionality that differentiates our product. Well, I have some great news for you. This is exactly what this course is all about. The patterns we're going to learn are universal and have already been successfully used by many companies. The best part about those architecture patterns is that they are implementation independent. So during the video lectures, we will mainly focus on the architecture and the general guidelines of each pattern. However, where applicable, I will also provide you with additional resources that will help you implement those patterns in your system. So now that we got some motivation, let's briefly talk about the difference between the patterns we're going to learn in this course and the famous design patterns that you've probably heard about, like the factory pattern, the singleton pattern, strategy, and so on. The so-called design patterns all came originally from a book published in 1994 called Design Patterns: Elements of Reusable Object-Oriented Software. As the name of the book suggests, those patterns are primarily targeted towards standalone applications implemented using object-oriented languages such as Java, C#, C++, or Python. What those design patterns help us achieve is better code organization within a large and complex codebase. By following those patterns, we can achieve better code reusability, extensibility, and higher developer productivity. However, while those patterns are very useful, they are limited to the architecture of a single application or library and are only applicable for object-oriented languages. But when we need to architect a large-scale system using multiple independently deployed services that are implemented by different teams and different programming languages, some of which may not even be object-oriented, those design patterns are not going to help us. Additionally, those patterns don't address things like performance, user experience, error handling, or processing large amounts of data or network traffic. So the patterns we are going to learn are very different and are going to target exactly those areas. Now, before we start learning our first software architecture pattern, let's talk about the biggest and most important pattern we're going to heavily rely on. And that is, of course, cloud computing itself, which came as a general solution to a problem that many companies were dealing with. The first problem that cloud computing as a general concept solves for us is instant access to virtually infinite computation, storage, and network capacity. This is commonly referred to as infrastructure as a service. Without the service, every company would have to spend months hiring specialists and building infrastructure to deliver the most basic online product to the users. Additionally, the cloud's pricing model charges us only for services that we use or hardware that we reserve. This removes the entry barrier for startups that otherwise would have to make prohibitively large financial investments up front. So essentially, just like any software architecture pattern, cloud computing solves a general problem and provides an on-demand infrastructure to any company, regardless of its product. But in addition to the basic access to computers, storage devices, and network, the cloud vendors also offer us a large set of tools and features that can improve our performance, scalability, and reliability just by using their services. One notable example is multi-region and multi-zone deployment. With multi-region deployment, we can run our system in different geographical regions. This allows us to bring our software physically closer to our users, which directly translates to lower latency, higher performance, and better user experience. Additionally, in each region, we can spread our system resources across multiple zones, which are commonly referred to as availability zones or isolation zones. Each such zone provides certain isolation guarantees when it comes to power supply and connectivity. By spreading our application or database instances across multiple zones, if one zone loses power or internet connection, our system can continue operating and provide services to our users as if nothing happened. So just by utilizing those cloud features out of the box, we can already enhance our system's performance, reliability, and availability without doing anything special to our software architecture or implementation. Now, in addition to the infrastructure itself, which includes virtual machines, network routers, switches, and storage devices, cloud vendors also provide us with a general platform for building software faster. This includes databases, message brokers, load balancers, monitoring and logging services, function as a service, and many other tools that we can get access to in just a few minutes. Don't worry if you're not familiar with some of those offerings, because we will talk about them in more detail in later lectures. However, with all those great benefits we get from using the cloud, there are also two major disadvantages or limitations that we need to address. The first is the fact that we don't ever own any of the infrastructure that our system runs on. This low entry barrier, which comes with the pay-as-you-go model, also means that as we scale our services and store more and more data, our monthly bill also gets bigger and bigger. So as a software architect, now in addition to the general quality attributes such as availability or performance, you also need to manage cost efficiency and profitability. The second disadvantage of cloud computing is that the infrastructure we rent to run our system is out of our direct control. What this means for us is typically we don't get the most high-end hardware, and every piece of hardware we rent has probably been in use around the clock for months or even longer by other clients. So every single server, router, or database instance we rent may die, freeze, or lose connection at any given moment, and there is nothing we can do about it. And the bigger our system is, the higher the chances are, statistically, that some part of it will fail at one point or another. So the job of architecting large-scale systems that run on cloud infrastructure can be thought of as building reliable systems using unreliable components. This means that our software architecture will have to account for reliability and handling failures a lot more seriously, which is why we will dedicate an entire section to that topic. So now that we got an introduction to the types of patterns we're going to cover, let's quickly summarize what we learned in this lecture. We first got the motivation for software architecture patterns and identified them as solutions to common problems and non-functional requirements that any system can benefit from. And we compared them to the object-oriented design patterns, which solve a different type of problem, one of code organization in one single application or library. And later, we talked about the unique features and benefits of cloud computing, which we will learn to take advantage of. And we also mentioned the disadvantages and limitations of cloud computing, which we will learn to address using software architecture patterns. I'll see you all in the next lecture.